similar to this question.
Okay.
Yeah. I just want to know how to go around working with this, because for the spherical shape for this, I've already know how to work along with it. Yeah, but with this, how to.
Actually, I think we solved that problem before.
Yeah, we solved this problem before. It's just that, I mean, it's just the approach. It's not solving the problem per se. Yeah, it's just the approach, how to really, with respect to the question, how to approach it. And so I don't want the working per se, but it's just the approach of it. I mean, now that it's an infinite line of charge with charge density, blah, blah, from the y-axis as shown, where 8.4 centimeter and say what is the value for exp, the x component of the electric field at point P. So I think my problem here is what formula will I go for? Okay. Okay, yeah. So, like here, do I go directly to E line since this is infinite line and start to work with this formula 2K?
Well, there are usually two ways to solve for
Yeah.
field. You either do superposition or you do Gauss's law. Why can we not use Gauss's law in this case?
Yeah, that's why I'm like.
I'm asking, why can't
Yeah, that's what I'm asking. Which one is appropriate to attack, and how, how do I go about it?
you? Well, why is it not convenient to use Gauss's law?
Yeah, Gauss's law I think, is convenient because this already has a cylindrical figure around it.
But, well, you have two wires, right?
Yeah, two infinite lines, two wires. Yeah.
So your field is not infinite.
Mm-hmm.
Do you understand that?
No.
When we had a dipole, for example,
Mm-hmm.
we had this form, for example, positive, and this form negative.
Mm-hmm.
How does the field look like?
How what?
How does the field look like?
The field. How does the field move? The field moves from positive. It moves from positive to negative.
No, it's stationary. It doesn't move, but yeah.
Yes, from positive to negative.
Like this.
Yeah.
But then here it curves like this.
Mm-hmm. Then it curves. Yeah.
So in this case, I cannot find a Gauss's law or Gauss's surface over which the field is going to have the same magnitude and be perpendicular to the surface all the time because it curves like this. Same idea with your two wires.
Mm-hmm.
They interact with each other as well.
Mm-hmm.
What are the charge distributions
The charge.
in the wires?
The charge distribution
Positive or negative?
is for one is negative and the other is positive. Lambda 1 is negative. This is the charge density. But they didn't really give the actual charge. They only gave the charge density. Lambda 1 and then lambda 2 is 9.9.
So if you look, this is sort of a from the top perspective. If you look at that, this is how the field is going to look like. And if you pick a cylinder, which in this projection would be a circle, will your field be always perpendicular? Obviously not. Here it's going to be parallel to the surface, here it's going to be perpendicular, and here it's complicated. So you cannot just integrate and say, oh, this is my charging close and this is how I go about it. I feel like this is not. The integration is simple. So second option to find fields is superposition, which is immediate fields. This is how you find the field. Find superposition.
And then superposition would be using this.
Well, you have formula for a field from infinite lines.
Yeah, from infinite lines.
So you apply it for the first wire, for the second wire, and then at perfect order.
Okay. Okay. So they are saying, so if they say it's a find a field at point P. Okay, point P, so it means you'll be using the E point formula. I mean the electric field at a point formula.
Electric field is always at a point.
Yeah, I agree, but we have variations of formulas here. We have electric field at a point, electric field at a line.
Not at a line. Electric field produced by
A line.
point charge by a line of charge
Okay.
by a sheet of charge. At point P, you don't have any charge.
Okay.
The field is produced by charges, right?
Mhm.
You have two charge distributions. Both are infinite lines.
Mhm.
So you can use formula for one line or the other line, and then get whatever you want.
Okay. All right. Yeah. I think that's the thing that's what confused me on the exam. I mean that alone. But the only thing is that we're not able to bring take the exam papers with us. So if we are taking it with us, then we would have gone through some discussion. But we didn't take it with us.
Would you go to Professor Podolsky's office somewhere if you want to look at things and discuss some problems?
Yeah.
I don't think he will give the paper away, but you can look at it.
Yeah. Maybe I can do that tomorrow because I have to email him asking for time.
I guess you can just show up with that.
Yeah.
I don't know what
Yeah. But normally what we do before we go there to him, we have to write him and then he can say, okay, come at this time. Yeah. Because there are so many people wanting to go to see. I don't know. Yeah, I think that's it. Except maybe you want us to, you have something that I said, except you have something else that you want to share, that you think I'm supposed to know or we're supposed to know.
Say it again.
No, I said, except you have, I said I'm okay with the explanation. Yeah, except maybe you have something else that you want to share. Okay.
I mean, you guys didn't have class after exam. I didn't really expect anyone to come.
Yeah,
You have no homework yet, no lecture.
I think we have like pre-lecture.
No, it's due tomorrow.
Yeah, tomorrow checkpoints. There are checkpoints for tomorrow. Yeah. Yeah, so those were another
Well,
things.
did you understand?
Yeah, except you want me to, maybe I can explain in my own words, then you will know whether I really grab the concept. Yeah, okay. This is the cross section of the two lines of charge, and then the top, you're looking at it from the top, and these are
Well,
the.
I started out with just saying that this is the how you look at dipole.
Mhm. Oh yeah, yeah. But these are the same. I mean, because we're looking at the lines. Because you're looking at the lines from this side, but when you look on the top, it will turn as a dipole. Okay, and these are the equal potential lines you drew. These are the equal potential lines, isn't it? The electric field lines. Okay. So I mean, one question. So which one of the lines that goes circular around the pole? Which of the lines that will run in a circular form around the poles? Is it the equal potential lines?
Equal potentials are the lines that are perpendicular to the electric.
Yeah, to the electric field, yeah. Okay. Yeah, okay. Yeah, so you said, I mean, in this case, we can use the Gaussian surface because if you use the Gaussian surface, the electric field lines will be parallel to the Gaussian surface instead of being perpendicular to the Gaussian surface.
Not necessarily. I'm just saying, for Gauss's law, you have the integral of E at the equal to Q over epsilon.
Close, yeah.
So you have this dot product here. So usually what you do to get rid of the dot product, you pick such a Gaussian surface that field is perpendicular to the area. Besides, you want your field to be constant at whatever area you're looking at. Because if the field is dependent on the area, you have to integrate. In this case, I think it's quite complicated pattern. But you don't know the equation how field depends on the area if you pick this as your Gaussian surface. And it's not uniform, so yeah, like I said, it's a function of the area. You'll have to integrate, which you don't know, and I don't know the function. So what it's easier to do is to pick
The formula, yeah. Superposition by using the formula for each of the lines.
So what you usually do, like I said, you pick field which is perpendicular to the surface everywhere, and hopefully it is either uniform around that surface, or at least it's a function that you can integrate, known function that you can integrate. In this case, you don't know the function, and it's not perpendicular, so the angle is going to be changing all the time. Because, like I said, if you pick in the projection, this is the Gaussian surface. Here, field is perpendicular. But for example, here, it's going to be parallel. And here, you don't know the angle at all.
The what?
You don't know the angle for this
Yeah,
one.
yeah. think that's all right. Because I have to go. I'm going to go and do my lab. And that lab report. Yeah. And let me just ask a question from the lab report. I want to ask one question. Okay, so I'm about to do my my equal potential and few lines to draw them. So what I've really been confusing me is that if I'm going to draw the few lines at 6 for 6 volts, is it going to be, am I going to take it the same way, like since this is one graduation, I'm going to just take it like this to bring it here?
Well, we'll just make sure that it's perpendicular to
Yeah, perpendicular to equal potential. Okay.
What was your charge distribution?
My charge distribution, I mean, at this point, it was 10.
What were your charges? Was it a
Okay.
point charge?
Yeah, this is a point charge and this is a line. Yeah. So I'm going to just draw this to come here, and then the next one will come here. Yeah. Because we're going to draw the field lines for 4 charges. 1, 2, 3, 4.
These are just the lines with equal potential.
Mhm.
This is not charged.
Yeah, these are equal potential lines. I know that. Yeah. But I'm saying that the electric field line, because he said we should draw the electric field lines for each of these equal potential lines.
Just means that we're going to be going into the order of the equal potential.
Okay. That means that I mean, it will go this way, and that.
I guess. I don't know, but I cannot remember like the chart, the field distribution. I could Google it.
Okay. Yeah, I think I have that, but just Google it.
Did they have the safe charge or opposite charge?
They have. You mean the point charge and the line charge?
Yeah.
Yeah, only the point charge had like 10 volts, and at the line charge it was 0.
And what were the sign on the charger?
This was positive, this was negative.
Negative? So this is usually outside. This is usually towards. So I guess it would. I would expect it maybe look something. maybe something like this. You have to look at
Yeah,
like the potentials.
yeah.
I don't know whether these curve or they go straight. Just an assumption.
Yeah, even if they are not straight, but the arrow tells you where they are going. The arrow at the end tells you where they are going. So
Well, it just have to make sure they're perpendicular.
to the equal potentials. Okay.
Those are equal potentials.
Yeah. And then there's another equal potential around the line, the infinite line of charge.
Just draw your field perpendicular to
Yeah,
whatever the
yeah,
lines you
yeah. Okay. Thank you. I'm going to work on that now. And then what is working on?